Welcome to the chapter on radiation heat transfer. In this session, we'll explore one of the most fascinating modes of heat transfer, radiation. Unlike conduction and convection, radiation doesn't need any medium to transfer heat. This is why we can feel the heat from the sun, even though it's millions of kilometers away. We'll break down how objects emit and absorb radiation energy, discuss key concepts like black body radiation, and introduce practical equations such as the Stefan-Boltzmann law. By the end of this chapter, you'll have a clear understanding of how thermal radiation works in engineering systems and how it influences real-world applications like solar panels, building insulation, and industrial furnaces. Let's dive in and make radiation heat transfer an easy and engaging topic to master. Before we jump into the details, it's important to be clear about what you'll be able to do after this session. Learning outcomes act like a roadmap. They tell you what skills and knowledge you should gain by the end. For this chapter on radiation heat transfer, we're focusing on key practical skills. You'll learn how to define view factors. These help us understand how much radiation leaves one surface and reaches another. You'll also practice calculating radiation exchange, especially between black surfaces, which are the simplest case. Then we'll step up to the radiosity method, which helps you handle more complex, realistic surfaces. You'll use relations between view factors to make your calculations easier and more efficient. We'll also see how radiation shields can reduce unwanted heat transfer, like a car sunshade that keeps your car cooler. Finally, you'll explore gas radiation effects, which is crucial for applications like combustion engines and industrial furnaces. Think of this slide as your checklist. By the end of the chapter, you should be able to confidently check all these off. 2. Introduction to radiation heat transfer. Let's start by understanding what makes radiation heat transfer unique. Radiation happens because of thermal energy emission. When objects get hot, they naturally emit energy in the form of electromagnetic waves. This is how you can feel heat from the sun, even though it's 150 million kilometers away. The key difference between radiation and other types of heat transfer, like conduction or convection, is that radiation doesn't need any material medium. It can travel through a vacuum. Perfect example is space, where there's no air, but the Earth still gets warmed by the sun. You'll also come across the term view factors, which simply tells us how much of the radiation leaving one surface actually reaches another. Think of it like how much sunlight falls on your face versus how much gets blocked by a tree. We'll go deeper into these ideas to help you calculate and visualize radiation heat transfer easily. 3. View factors. Now let's simplify the idea of view factors. Imagine you have two surfaces in a room. How much of the heat leaving surface 1 actually reaches surface 2? That's what the view factor tells you. It's like asking, if I shine a flashlight from surface I, how much of that light hits surface J? There are two handy shortcuts to make calculations easier. First, the reciprocity relation. This shows that the view factor isn't one way. If surface 1 sends radiation to surface 2, surface 2 also sends radiation back, but proportionally based on their areas. Next is the summation rule. Everything leaving a surface has to go somewhere. So if you add up all the fractions going to every other surface, it must equal 1. Finally, there's a clever graphical trick called the crossed strings method. This is super useful for 2D shapes. It helps you find view factors by just counting how strings cross between lines. Think of it as a visual cheat code to avoid complicated math. 4. Radiation heat transfer between surfaces. Let's break down how surfaces exchange radiation heat. We'll start with the simplest case, black surfaces. Black surfaces are perfect emitters and absorbers, and their heat exchange follows the Stefan-Boltzmann law. The equation involves the temperatures raised to the fourth power, so even small temperature changes can lead to big heat transfer differences. In more complex systems with multiple surfaces, we use the enclosure equation to sum up heat exchanges. But most real-world surfaces aren't perfect. They are gray, meaning they reflect some radiation. This is where the concept of radiosity comes in, which is simply the total radiation leaving a surface, both emitted and reflected. To solve these problems efficiently, we introduce the idea of surface resistance and space resistance. Surface resistance depends on how emissive the material is, while space resistance depends on the view factor between surfaces. A very helpful tool is the radiation network method. Think of it like analyzing an electrical circuit. Radiosity plays the role of voltage, and resistances behave like electrical resistors. This analogy helps you visualize and calculate radiation transfer more intuitively, especially in complex systems. 5. Radiation shields. Let's talk about a simple but powerful way to reduce unwanted heat transfer: radiation shields. The concept is straightforward. By adding a barrier between two surfaces, you increase resistance to heat flow. Just like wearing sunglasses reduces glare, a radiation shield reduces the heat moving from one surface to another. In fact, adding just one shield can cut radiation heat transfer almost in half, about 50% reduction. And if you add more shields, the effect compounds. There's a simple formula for this. With n shields, the heat transfer becomes the original amount divided by n plus 1. This concept isn't just theoretical, it's applied in the real world. Radiation shields are used in cryogenic systems to keep things ultra-cold, in precision thermometers to prevent heat interference, and in furnaces to control heat flow. It's a simple tool with big energy-saving benefits. 6. Radiation effects in temperature measurement. Let's look at a common problem. Temperature readings can be misleading when radiation interferes. If radiation from surrounding hot or cold surfaces hits a thermometer, it can cause the thermometer to read incorrectly. This is why you sometimes get strange readings near furnaces or cold walls. To fix this, we use a correction formula. It adjusts the measured temperature by accounting for the radiation effect, especially when the surrounding wall temperature differs significantly from the object you're measuring. The practical solution is simple. Use a low emissivity radiation shield. This shield minimizes radiation interference, allowing the thermometer to focus on the real temperature of the fluid or surface, not the heat coming from the surroundings. It's a small adjustment that makes your readings much more reliable. 7. Gas radiation. Participating media. Let's wrap up by looking at radiation from gases, which is a bit different from solid surfaces. Some gases, like air, nitrogen, and oxygen, are non-participating. They don't interact with thermal radiation. They're basically invisible to it. But gases like CO2, H2O vapor, and soot do participate. They absorb and emit radiation, especially in combustion environments. To handle this, we use Beer's law to calculate how much radiation gets absorbed as it travels through gas. Next, we calculate gas emissivity, which combines the emissivity of CO2 and H2O, adjusting for overlaps. This helps us understand how much radiation the gas actually emits. When calculating heat transfer between gases and surfaces, we use different formulas for black and gray surfaces. For black surfaces, it's a direct calculation, but for gray surfaces, especially when emissivity is above 0.7, we adjust the formula to reflect realistic surface behavior. This understanding is crucial in industries like power plants and combustion systems, where gas radiation can make a big difference in thermal performance. 8. Applications of radiation heat transfer. Let's end by connecting radiation heat transfer to real-world applications. First, in industrial furnaces, gas radiation plays a big role because of the extremely high temperatures. Understanding it helps optimize heating efficiency. Next, in spacecraft insulation, engineers use multi-layer radiation shields to prevent overheating or freezing in space, where there's no air to conduct or convect heat. Only radiation matters. In buildings, HVAC designers have to account for radiation effects to maintain comfortable indoor temperatures without wasting energy. Finally, even our own bodies are part of this story. Human body heat transfer involves not just convection and evaporation, but also radiation. That's why you feel warm near a fire even without touching it. Learning these applications shows how radiation heat transfer is not just theory, it's everywhere around us. 9. Summary. Let's wrap up with a quick summary. Radiation heat transfer mainly depends on three things: emissivity of the surface, view factors, and temperature difference. The higher these values, the more heat is transferred. To make things easier, we often use simplified models like gray and black body surfaces, so we don't get stuck in complicated calculations. Radiation networks help us visualize heat transfer like electrical circuits, making analysis more intuitive. Radiation shields are a simple but powerful way to cut down unwanted heat transfer. In high-temperature environments, participating gases like CO2 and H2O play a big role in radiation exchange. And, most importantly, these concepts aren't just theory. They're applied in furnaces, insulation systems, and even in keeping people comfortable indoors. Mastering these basics will make your engineering design smarter and more energy efficient.